Hello everyone, today let's look like a QP137 with some more properties of Poisson processes. So in part A, we're just deriving the mean and variance of the exponential distribution. In part B, we're deriving the mean and variance of the gamma, which shouldn't be too hard once we know part A. And then in part C, we're just proving probably the most important part of the exponential distribution, the fact that it is memoryless. So let's start in part A. Let's let x be an exponentially distributed random variable with rate parameter lambda. If so, we know the PDF of x from basically QP111 is just going to be equal to lambda times e to the power of negative lambda x. So for part A, we could do it one of two ways. We could either use the moment generating functions, or we could just derive it the old-fashioned way. So I'll do it the old-fashioned way first, and then we'll do the moment generating function way. So the definition of expected value when our function is continuous, right? Exponential is a continuous distribution, obviously. So we're going to be going from 0 to infinity because x can take values from 0 to infinity. That's again because the exponential models the wait time between events in a Poisson process, right? So if we have x right here, it's going to take values between 0 if the event happens instantly, or infinity if the event never happens or it takes forever to happen, right? So I'm just summing over all the possible values that x can take. An integral is like a sum, but just continuous, right? X times the PDF, right? So lambda times e to the power of negative lambda x. And we are summing up over all possible values of x. We're integrating with respect to x. That means I can pull my lambda out because it is a constant relative to what we're integrating over. Now for this integral right here, I'm just going to basically use integration by parts. So I'm going to set u equal to, basically, let's set u equal to x. That means du is just going to be equal to 1 times dx, so just dx. So now if we set dv equal to e to the power of negative lambda x, we know that v is just going to be equal to, well, it's going to be equal to 1 over lambda, negative 1 over lambda times e to the power of negative lambda x. So some integration by parts action. I know I take vu minus the integral of v du. So what is vu? Well, it's just going to basically be x times negative 1 over lambda. So I'll just say negative x over lambda times e to the power of negative lambda x. That was vu. Now we subtract the integral of v du. So when we do that, these negatives are going to cancel. So I'm just going to get plus basically the integral of v du in this case, which is going to be 1 over lambda times e to the power of negative lambda x dx. So by integration by parts, we decompose this into this. Now we still have that lambda out front that we can multiply by conveniently to get rid of these lambdas down here. So when we do that, we're going to just get something that looks like this. And again, right here, we're taking the integral from 0 to infinity again. So now we can do this. This is just going to be equal to, well, this thing right here is just going to be equal to negative 1 over lambda times e to the power of negative lambda x, obviously evaluated from infinity to 0. So in totality, if we have this term on 2, we have negative x times e to the power of negative lambda x minus 1 over lambda times e to the power of negative lambda x. All of this evaluated from infinity to 0. Now if we evaluate this right here, if we take the limit as x goes to infinity of this term, it's going to be 0. If we take the limit as x goes to infinity of this term, it's also going to be 0. So this is just going to be equal to 0 minus, now we have to evaluate at 0. So this term right here, evaluated at 0, is just going to be, well, 0. And then we're going to have this term over here. So 0 minus negative. When we plug in 0 over here, this is going to be a 1. And we're going to get 1 over lambda in here. So it's going to be negative 1 over lambda. So just equal to 1 over lambda. So that's the expected value of an exponentially distributed random variable. So I'll say the expected value of x is just equal to 1 over lambda, which makes a lot of sense. This makes a lot of sense because this lambda is a rate parameter. So for instance, it might be like 1 dog barks per hour. So if we take 1 divided by that, that would just mean that we expect the waiting time until a dog to bark to be 1 hour, right? 1 divided by 1 per hour is just 1 hour. Now probably the easier way to solve this, and definitely the easy way to get the variance, is if we just do the MGF, right? We take the moment generating function. So to do that, we just need to take the expected value of e to the power of tx. Why? Because this is going to be a power series that we can differentiate to get the moments, right? That's what a moment generating function is. We've been over this. So this is going to be pretty simple to calculate in our case. We have the integral from 0 to infinity of e to the power of tx, and then our PDF was just lambda. I'm just going to pull that out because it is constant relative to our iterator, basically, or what we're integrating with respect to, times e to the power of negative lambda x dx. We know properties of exponentials. We can just rewrite this as basically e to the power of t minus lambda times x, right? Now this is very simple to integrate. We're just going to have lambda times basically 1 over t minus lambda times e to the power of t minus lambda times x, basically evaluated from infinity to 0. Let me make some more room. Okay, so let's keep going right here. Let's pull out our constants and let's evaluate our first term at infinity. So how do we do that? Let's just take the limit as x goes to infinity of what's it going to be? E to the power of t minus lambda times x. So now we need to subtract off this evaluated at 0. When we evaluate this at 0, it's obviously going to be 1. We already pulled our constant out, so we're just going to have a minus 1 here. Now, as x goes to infinity, this is only going to go to 0 right here. Basically, when lambda is greater than t, because then t minus lambda will be negative. So we essentially just need lambda to be greater than t here for this to be 0. But basically, you know that when we take the MGF, we're basically just going to be evaluating stuff at 0. So we just need lambda to be greater than 0, which is basically true all the time because lambda is a rate parameter. Therefore, for all intents and purposes, we can just say that this term right here is 0 because we're only going to be evaluating at t equal to 0. So then now when we plug this in, we're just going to take the negative of this. So we can basically just flip the bottom part and just say it's going to be equal to lambda on lambda minus t. So this is my MGF, so I can differentiate and evaluate at 0 to give me my moments, right? So the expected value of x is going to be the first derivative of this evaluated at 0. The first derivative of that is just going to be lambda on, let's see, lambda minus t all squared, and then we need to evaluate that at 0. When we do so, we get basically lambda divided by lambda minus 0 squared, so lambda squared. So again, that's just going to be 1 on lambda, which we already got. Okay, now finally, to calculate the variance, well, we know the variance is just equal to, the variance of x is equal to the expected value of x squared, so the second moment, which you can get using the MGF, and then we need to basically, what do we need to do? We need to subtract off the expected value of x all squared like so, which we already calculated. So the expected value of x squared right here is just going to be 1 on lambda squared. So it's just going to be 1 on lambda squared. Now we know the second moment we get by getting the second derivative of the MGF. In this case, it's just going to be the first derivative of the first derivative of the MGF, obviously, which is just going to be, in this case, you can do it however you want, but you're going to get 2 lambda basically on lambda minus t cubed. You evaluate this at t equals 0 to get the second moment, and when you do so, you get 2 lambda on lambda cubed, so that's just going to be equal to 2 on lambda squared. Now when we subtract off 1 on lambda squared, we just get 1 on lambda squared. Okay, so the variance of the exponential is going to be 1 on lambda squared, and the mean or the expected value of it is going to be 1 on lambda. Okay, that was a lot of calculus for no reason, but basically now what do we know? We know that if x is an exponential random variable, this is its PDF, this is its expected value, 1 over lambda, and its variance is 1 over lambda squared. So now let's do b, which should be very easy once we've done part A. So what you could do is find the MGF for this density and then differentiate it at 0 to find all the moments basically, and then calculate your expected value and variance that way, but we don't have to do that. If you remember back in QP 126, we derived this density basically from the fact that we are modeling the nth arrival in a Poisson process. The difference between this density and what we derived in QP 126 is just this gamma function, which just basically generalizes this is equal to k minus 1 factorial if k is an integer, right? So we're just generalizing k to non-integer values. So that's why what we derived looks different, but for all intents and purposes, this is just k minus 1 factorial here. So if we have our Poisson process here, right, this represents time, and then we have our first event in our Poisson process occurring, and then maybe we have our second event, and then we have our third event, and then maybe we have our fourth event. And with this density right here, the gamma distribution, we're modeling the wait time until basically the kth event. So gamma is the wait time until the kth event in a Poisson process, but all we have to do is realize that the time between all of these individual events are just going to be exponentially distributed, right? Because the exponential is the wait time until the first event, or it's also known as the wait time between two events. So if this is my Poisson process and I start at t equals 0, then my wait time until the first event is going to be exponentially distributed. And then right when I get my first event, my wait time until my next quote unquote first event, but in this case it's our second event, is also going to be exponentially distributed. So this one's exponentially distributed with rate parameter lambda, right? This one's also exponentially distributed with rate parameter lambda. And then boom, right when I get to my second event, I'm going to have basically exponential wait time until my next quote unquote first event. In our context, it's our third event. So right when I get to my second event right here, it's basically like I'm restarting the whole Poisson process from that exact point where my second event happens. And then we know that we are going to have an exponential wait time until the first event of that process, right? So this is just exponentially distributed with rate parameter lambda as well. So the wait time between events in the Poisson process is exponentially distributed. And basically the wait time until the kth event, that means it's just going to be the sum of all these exponentially distributed random variables with rate parameter lambda, the waiting time between each of our events. So if k is equal to 4, the wait time until the kth event, in this case the fourth event of the Poisson process, is just going to be the sum of 4 exponential random variables with rate parameter lambda, right? It's just going to be their sum. So what we can say, therefore, is that the expected value of a gamma distributed random variable, basically with parameters k and lambda, those are our two inputs, is just going to be equal to the sum from I equals 1 to k of basically an exponentially distributed random variable with rate parameter lambda. So sorry, we can write this gamma as basically this right here. So if we take the expected value of it, well then we take the expected value of this term over here, and look, we can use linearity of expectation right here. We know that this is just going to be equal to the expected value of an exponential with rate parameter lambda on the inside of the sum. And in part A, we just showed for this question the expected value of an exponential with rate parameter lambda is just going to be 1 over lambda. So all we're doing here is we're summing k basically of 1 over lambda. We're taking the sum from I equals 1 to k of basically 1 over lambda. So we're just summing a constant k times, so this is just going to be equal to k over lambda, and that is the expected value of a gamma distribution. Now let's come down and find the variance, where we can basically do relatively the same thing. So one more time, if x is a gamma with parameters k and lambda, and y is an exponential with parameter lambda, well then we just showed that we can express basically x as the sum from, let's say, I equals 1 all the way up to k of basically y sub I. So now if we want to find the variance of x, we just have to find the variance of this sum right here. It's just going to be equal to the variance of this sum, where we're going to plug that in. So we're taking the variance of this sum of our basically exponential lambda random variables. And again, we're modeling a Poisson process here where we have independent events occurring at a constant rate. So therefore, the waiting time in between them is also going to be independent of each other, right? That's because events are occurring at a constant rate. So no matter how long our first wait time is, right, it's not going to affect basically the distribution of our second wait time, which is not going to affect the distribution of our third wait time, etc. So because all these are independent, we know that from QP41, we can basically just express this just like we did with the expectation, basically as the sum from I equals 1 to k of the variance of y sub I. So for linearity of expectation, right, we don't even need independence, even though in this case they are independent. But for variance, right, if we do linearity of variance, they have to basically be independent. Now, all of these y's are distributed as an exponential with rate parameter lambda. And we just showed in part A that the variance of an exponential with rate parameter lambda is just going to be 1 on lambda squared. So we can just plug that in right here. So all we're doing here is we're taking the sum from I equals 1 to k of basically 1 on lambda squared. So again, this term right here is constant with respect to our iterator. So this is just going to be equal to k divided by lambda squared. So this right here is a variance of the gamma distribution, right, when k is an integer. It turns out when k is not an integer, these are the exact same as well. So again, just because the gamma, we're modeling a Poisson process, we can just use the properties of a Poisson process to calculate these a lot easier than what we'd have to do with the, basically we'd have to take a huge integral of that PDF, which is probably the most complicated PDF of any function, right, or of any distribution. So yeah, here's the expected value of a gamma, and here is the variance. So now let's go on to part C. Okay, so part C, the most important part about the exponential distribution is the fact that it is memoryless. So if x is an exponential random variable with a rate parameter lambda, like it is here, well then it's going to have this density. First of all, this is our equation right here that we have to prove, so let's think about what this means visually. We know that x is going to basically model the wait time between basically when we start in the first event in a Poisson process, or you could think about it as basically the wait time between events in a Poisson process. So x represents a time, the wait time between events, so the probability that x is greater than s plus t, given that x is greater than s, and we're trying to prove that that is just equal to the probability that x is greater than t. So we know conditional probability, right? If we're given that x is greater than s, well, let's say s is right here. So we're given that we've already waited s seconds basically. And now once we're given that, we want to find the probability that x is greater than s plus t. So maybe s plus t is right here, in which case the difference between these events is obviously just t. Basically what we're saying is, given that we've already waited up to the point s, what is the probability that x is greater than s plus t, right? So what is the probability that we actually end up waiting this amount of time somewhere in this region right here, given that we've already waited this amount of time? So first way to solve this is just, we can just use basically the definition of conditional probability. We know that this is just going to be the same thing as basically we're going to have that divided by the probability that x is greater than s, and then on top we're going to have the probability that x is greater than s plus t, and basically x is greater than s. This is just the definition of conditional probability. So up here all we're saying is, what is the probability that our first event comes after s plus t and it comes after s? Well, we know that if it comes after s plus t, well then it must come after s, right? So this is just the same thing thing is saying the probability that x is greater than s plus t. Okay, so now let's just calculate these two probabilities. Let's start on top. What is the probability that x is greater than s plus t? So a first event occurs after the time s plus t. Now we can do this the exact same way that we did QP 111, right? What is the probability that x is greater than s plus t? So what's the probability that we fall right here? Well, this is a Poisson process, right? So it's just going to be equal to the probability that we basically have 0 events throughout the first s plus t amount of time. So we want 0 events to happen right here, and then we know that after this, the next event will happen somewhere after s plus t. So that's just the probability that our first event is greater than s plus t is equal to the probability of no events up to the point s plus t. So again, just to write it out more formally, this right here is just the probability that a Poisson random variable, which I'll call y, is equal to 0, where y is basically distributed as a Poisson with basically rate parameter t plus s times lambda in this case. So we just plug into the Poisson PDF, which we again derived in QP number 1. When we do so, we just get e to the power of negative basically t plus s times lambda. And now on the bottom, what is the probability that x is greater than s? Well, again, we can do basically the exact same reasoning. The probability that our first event comes after s is just equal to the probability that we have 0 events in our Poisson process up to the time of s. So 0 events in here. So again, that's going to be Poisson distributed. We know the PDF of the Poisson. When we plug in our rate parameter is basically going to be s times lambda, just like we did again in QP 111. So this right here, this probability is just going to be e to the power of negative s times lambda. So this is what we're calculating right here. We know by laws of exponentials, we can just break this up into basically e to the power of negative t times lambda times e to the power of negative s times lambda, and then we're dividing that by e to the power of negative s times lambda. So these are going to cancel right here, and we're just going to be left with e to the power of negative t times lambda. So the probability that x is greater than s plus t, given that we're already greater than s, is just going to be equal to e to the power of negative t times lambda. But what is this also known as? Well, this right here is just equal to the probability that basically x is greater than t. Why is that? Again, from QP 111, it's coming up a lot, but the probability that x is greater than t is just going to be equal to the probability that we have 0 events all the way up to the point t, which is Poisson distributed with this PDF that we derived from QP number 1. Now we've shown what we needed to show, but why is it important? Well, the exponential, first of all, is the only continuous distribution that basically has this property. So if we drop in some random point along our Poisson process s, it doesn't matter where, it could be anywhere random, right? S was chosen arbitrarily. So all this equation right here is saying is that given that we dropped in at this point s, basically the probability that x is greater than s plus some event t is completely independent of s, right? It's just going to be equal to the probability that x is greater than t. There's no s in this final formula right here. So again, one more time, what memorylessness is saying is that no matter where in our Poisson process that we start waiting for our next event, right? No matter where we start, it could be at any random point s, the probability that we have to wait basically longer than t is just going to be completely independent of s, right? So even if I've been waiting for 1 trillion years, let's say s is equal to 1 trillion, well then the wait time until my next event is going to be the same basically regardless of how long I've been waiting. I could have been waiting for 1 trillion years, a quadrillion years, 1 second, 2 seconds, it's going to be the same. So again, no matter what amount of time that I've already been waiting, the wait time between when I start watching right here and basically s plus t is just going to be an exponential with parameter lambda t. That's how my wait time is going to be distributed regardless of how big s is. So in QP 136 this is actually going to be useful, and it's going to maybe make a little bit more sense than it does right now, but that's basically memorylessness, and it's the most important property of the exponential. It's the only continuous distribution that is memoryless.